Howdy, Chapter 10, Momentum. At this point, you should be an expert in specifying a system, drawing a free body diagram showing the forces that act on the system, from the details of the force, figuring out how to solve any problem. If a force acting on a body is unknown, it would seem like there isn't much that can be done towards getting a solution. In fact, in this chapter, a law is developed that either totally or at least partially can be used to solve for an object's motion even when there are unknown forces present. This powerful law is called conservation of momentum. It is much simpler than the development of potential energy functions and conservation of energy, and it is extremely useful. The first step in developing this law is to define the center of mass of a system of objects. The object can be molecules, planets, some blocks, or anything else. It is then shown that everything we have done up to now in this course really involved the motion of this point called the center of mass. When we had a block sliding down an inclined plane, we never worried about its dimensions. We were considering the block to be a point. In fact, everything we did works just as well for real blocks as long as we remember that it is the motion of the center of mass of the block we are finding. We then defined P, a vector, the momentum, sometimes called linear momentum of an object, as its mass times its velocity vector. The vector P equals m vector v. For a system with more than one object, the total momentum is just the sum of all the individual momentum vectors. Using Newton's third law, we will get the fundamental result. The external force on a system is the time derivative of the total momentum vector of the system. The law of conservation of momentum then states, if the external force on a system is zero, the total momentum of the system is a constant. Since we are dealing with vector quantities, the law holds for any component of the total momentum if the corresponding component of the external force is zero. If, for example, there is no force only in the x direction, then F external x component equals zero, equals the time derivative of the x component of the total momentum. And P total sub x is therefore a constant, even if other components of the momentum are not constant. The law can be applied to all kinds of processes such as collisions or explosions. It will be shown that some information can be obtained when there is a collision in one or two dimensions, even when the force between the colliding objects is unknown. What we have here is an air track so that these two carts can move essentially without friction along the track. If we call this the x direction, the law of conservation of momentum will tell us no external force in the x direction. The total momentum of the system is independent of time. So can we predict what will happen if I send these two carts at each other, for example, with the same speed, so that the size of their momentum are equal, but they're oppositely directed? The total momentum is originally zero. What will happen afterwards? In fact, we can't predict what will happen. It depends on the interaction, on the force that one of these carts exerts on the other. At one extreme, we have a perfectly elastic collision, no loss of kinetic energy. The two carts should go up equal but opposite momentum to what they came in at. Obviously exactly correct. At the other end of the extreme is Velcro on each, so that when they collide they will stick together. Because they stick together and the total momentum has to be zero, they must come to rest, which they do. Of course, in nature you can have anything in between, not perfectly elastic and not totally inelastic. What will happen if one of the masses is much heavier than the other. We've added a few weights to one of the carts. Perfectly elastic collision, we can still calculate what will happen because there's no loss of kinetic energy, together with total momentum in the x direction being a constant. What should happen is the heavier cart should go off with a loss of momentum. The lighter cart should pick up momentum. Obviously that works. Final demonstration would be a heavy object colliding with a light object, like a garbage truck, and a fly, or any bug, sticks to the windshield. The momentum of the heavy object will hardly be decreased. The fly will then, of course, be stuck to the windshield. This is not a garbage truck and not a fly, so that won't work exactly correct. The fly is now stuck to the windshield. What about two-dimensional motion? We can use the law of conservation of momentum to predict what would happen, for example, on a pool table. I won't demonstrate it, but you can go over to the MSC and watch some fellows playing pool. They calculate in their head, px before must be px after, py before must be py after, perfectly elastic collision. 3 simultaneous equations tell them if the black ball goes in that pocket, will the white ball go in that pocket. They do the calculations in their head. They should be studying Physics 218. They probably will fail the course. Gig 'em. Summary. The center of mass of a system of objects is defined. This important quantity lets us understand why it was useful to treat all objects as points in the previous chapters. The momentum vector of an object is defined. It is shown that for a group of objects, F external equals the time derivative of the total momentum of the system. Total momentum is a constant if there is no external force acting on a system. Gig 'em.